Sure. But
Or don't behave. It's also just as fun.
You know that knight is the German knecht, which is also a servant.
Exactly. Oh,
So,
okay, 1 second, because it just takes. Once it starts, then I have to mute on the other side. Otherwise, we have repeated.
sure.
There you go.
It's early in the morning at your side, Egon, right?
Sorry?
It's early in the morning at your side.
No, it's 9 o'clock.
Oh, okay, it's good, good.
That, we call that early morning here.
I'm usually up at 7.
Oh, I'm dreaming at 7 about you.
You mean you're misusing English again? You meant nightmares.
Exactly. Well, it's good dreaming, yeah.
I think Hiro, details stay with you, okay?
Sounds good. Sounds good. All right. We're very close to the time, but anyway, so I put this on this real quick. People are showing up. I don't know if I have anybody else that time. Okay, well. Yeah, I think it's anybody else that I need to promote that I see. No, so far not. Rick is there, that's good. Okay, so I think we are on time now. So once again, I welcome everybody to join us to the online SPICE-SPIN+X seminar series organized here in the Spin Phenomena Interdisciplinary Center by myself, co-lead with Libor Schmekiel, Angela Wittmann in the organics, and Karen Eversosite, who is now at Duisburg University, in collaboration with the Collaborative Research Center of Spin+X, led by Martina Schliemann and Burkhard Hillebrands in Kaiserslautern, and Matthias Chloe, here the speaker of Spin+X in Mainz. This is a Zoom webinar, as we all know, so you can see the speaker at the time, and but you can raise your hands or write a question in the Q&A, and I will give you the floor after the talk usually, but it's an important question. I can do it before. And just as a reminder, that it's always at 3 p.m. And then we will have a few talks the next week with Alberta Benoni and Angela as well, and some other ones. Please check out the, hopefully with titles, we'll have eventually the titles for next week's. And then they become immediately available on YouTube, as you all know as well. Just to introduce the speaker today, Stefano Sanvito doesn't need much of an introduction. He's a very well-known, one of our most well-known condensed matter physicists in Europe here in the Trinity College in Dublin, and director of CRAN. He studied in University of California, Santa Barbara, Lancaster University, and University of Milan. They did reverse order. I think University of Santa Barbara as a PhD. And then has developed many algorithms, both in material science and across the scales, in a very range of different physics that we've overlapped in the past overall, and now focusing a lot, or particularly on new ways of computation and looking at neuromorphic type of schemes. He has many awards, but one of the ones that I find absolutely cool, that he's a knight. And also we have Sir Stefano with us today. A knight of the Star of Italy, you know. So he's not only we have this in the stardom. So with that, I'm going to ask you to please go ahead and share your slides, and we're very much looking forward to your talk. And then we'll mute ourselves in there to give you all the bandwidth.
Can you see it?
Yeah, we see it very well. Go ahead.
Okay, so let me also magnify. Can you see my pointer as well?
Yeah, we can see the pointer. Yeah, and then you probably correct. Yeah.
Okay. All right. Okay. So yeah, thanks a lot, Yaro, for the introduction, and all the organizers of the series for the invitation. So I'm very happy to be here. Virtually here and everywhere, I guess. I understand. So what I'm really going to talk today about is a series of methods that we have been developing in the last few years. To try to accelerate material discovery. And of course, because of the series, I'm really going to focus on magnetism, although a lot of the methods we're developing are not so magnetism specific. Well, before I would like to acknowledge all the members of my group, and I'm going to point the various contributions as the talk goes along, and a bunch of various funding agencies that at any given time has provided funding. Okay, so what is the idea here? What is the message I want to convey? I just want to try to explain how, from the theory point of view, at least, we can try to develop what I called a solution for an inverse problem. So let me try to explain what I mean. So let's suppose you want to design a magnet that has a certain number of properties, right? And because you have in mind a specific application. Typically, what you would do is what you have available is a very large chemical space and structural space. So you have a periodic table to play with, and you can arrange the atom in any way you possibly want. Typically, your knowledge is limited to some pocket of this very large chemical and structural space, which is, of course, is a multi-dimensional space. And essentially what you know is, some material which exists, the property of this material, say, I don't know, in this case, the Curie temperature or the magnetocrystalline anisotropy. But the question actually, if this particular material that is not suitable, or the technologies move on, so it's no longer suitable, the question is how you would find a new one. And the typical way we do that is we try to go around what we know. So we try to modify the material in the way that physics and chemistry allow us to do it. And essentially, we always try to explore relatively close region of where we are. And really, we try to essentially, the trial and error method is, well, try to go somewhere where you think you find something good, and then measure the property and see whether the things work. Of course, it would be much, much more interesting if you can do the inverse process. So if somehow you have a knowledge of how the property change across structure and chemistry, and then point the particular region of chemistry and structure that optimize the property you're looking at, and then try to grow. And somehow, actually, we have a heuristic method to do this. This is called physical and chemical knowledge. We know that some crystal structures are prone to some properties, some other are not. But the question actually, can you do this in a systematic and precise way, where actually the shot you have at the growth of a particular material have a high probability to succeed? So that's essentially the idea. And so there's not a clear solution to this problem, except that what you need to do, you need to really try to explore, at least from the theoretical point of view, the larger structural chemical space and find regularity in this. And to do that, you need to design a pipeline or computational method that allow you to have the throughput needed to do this exploration, which can be what we're talking about here is actually many millions of different potential structure and chemical composition. So what is essentially the task you have what is essentially the general philosophy? Essentially, you have to check 4 different steps in a ladder. So first one, you need really to explore the chemical space. And again, as I said, you have a periodic table to play with. And I'm going to show you in a second that it is really the periodic table. There is actually very little discount you can do on that. Then you have to explore the structural space. And again, you have a 220-something space group to play with. And then you can arrange the atom in the space group in many ways you want. So that's a very large space. Once you have identified what is possible chemically and structurally, then you need to try to associate properties. And then finally, and this is actually valid for some number of applications, the properties themselves are not so useful unless you compare them with the environment the material is used in. Think about a magnet. Of course, a magnet, the property of a magnet depends on the temperature, which is a way to define the environment. Or you might have, if you want to deploy, say, a magnet in a harsh environment, and this magnet doesn't need to be just a good magnet, but need to be a magnet, for instance, that withstand corrosion or other environmental attack. So that's actually the complicated problem. And essentially, the strategy that we have is actually quite, wrong way, is relatively simple. What you really need to know is to have methods which are very fast at screening the lowest part of this diagram. So where we have a lot of combination, and then they become slower and more refined as we go up. So in other words, the idea is to funnel materials, at the beginning explore as much as we can and as fast as we can, decide that some of them are in the range of properties that we're interested in, and then tune in the computational strategy as we identify new material. And of course, what you do is as you grow, as you walk along this ladder, you carry on less and less materials, but then you do the calculation at the increased level of accuracy. So that's essentially the idea. And of course, we are theorists, but at the end of the day, you can do as many predictions as you like, but if you don't go to the lab to try to verify them, this is pretty much useless. So at the end, you need to be able to have a colleague to point to who is going to try to make those material you predict. So that's essentially the idea. Now, I'm going to show three different ways to somehow go along this ladder. The first one is we try to decide that we want to look for a property, and this property is the Curie temperature, and I'm going to explain in a second why is the Curie temperature. And then what we're going to do, we're going to try to explore the chemical space. So essentially, the question we're going to ask is, what chemical composition are most likely to generate a magnet with a high Curie temperature? The second example I'm going to show is to construct now more accurate models that essentially try to answer this question: where should I put the atom in such a way to maximize the magnetic crystalline anisotropy? And I'm going to take singular molecular magnet as an example. And the last things I'm going to show you is still in the same vein. We try to design a force field that describe on the same footing all the possible magnetic excitations that you can have in a magnet. So then we can really have accurate description of transition temperature and so on, even for a situation where it's not clear what is the dominant method of excitation of a particular magnet. So that's essentially the idea. And so let me go to the very first topic, and is the one of predicting Curie temperatures. And before I do that, I just would like to give you a quick kind of overview of how many magnets we actually know, okay? So this histogram that I'm showing here is an histogram of Curie temperature of known ferromagnetic material. Here I'm just concentrating on ferromagnetic, so I'm not looking at antiferromagnetic or ferro or any other kind of magnetic order. I'm just looking at pure ferromagnetic. And if I count only once metallic alloys with different compositions, so I don't list any single possible composition, I have about 2,500 of unique magnetic compound. Now, if you look at this histogram of the Curie temperature, you find out that most of the Curie temperature actually are in the lower range. So essentially, there is actually not so much above, say, 600 Kelvin, which is roughly where you should put your Curie temperature if you have in mind the application for everyday use, say an hard disk drive, for instance. The other thing I want to stress about magnetism is the periodic table you see here. The elements are color coded with abundance of a particular element in any of these 2,500 magnets. So in other words, actually, it's the frequency at which elements appear in magnet. And as you see that overwhelmingly, you have the most magnets are made of iron, cobalt, manganese, and nickel, and oxygen, because of course, there are a lot of magnetic oxides. But you also have a good participation of the rest of the transition metal series, of a 4D metal as well, some of the heavy metal, but actually rare earths, of course, but then actually, except for noble gas and very little else, more or less every element in the periodic table somehow feature in a magnet of some kind. So magnetism is really something that involves the entire periodic table. As I said, 600 Kelvin is the critical temperature for magnet. And as you see, beyond 600 Kelvin, there is an awful lot. And I just want to stress that it's really true. So, and a lot of this magnet, which has a Curie temperature above 600 Kelvin, have been known since a long time. Iron, for instance, and some of the elemental metal. Now, just to give you a feeling of 2,500 magnet, what actually means, the first report that I know about of the existence of magnetism actually was reported in a book written in 79 AD, okay? And this actually is part of a Historia Naturalis from Plinius the Elder. Plinius the Elder was a general of the Roman army, was an admiral of the Roman fleet, actually, who wrote this book about natural history, and he reported of a legend of two stones attracting each other. So that was probably the first written evidence of magnetism that I know about it. And, you know, this was written 2,000 years ago. So in 2,000 years, we discovered 2,500 magnets. Okay, so the rate of discovery is not gigantic. So finding a new magnet is not an easy task. Okay. Now, the other thing I want to mention is, just for the record, that this table of magnet has been compiled manually. So essentially, we produce this database of ferromagnetic temperature of magnet by looking in the literature, one paper by one paper, and books and so on. And this is a complex thing. Now, what we're going to show you how you can construct machine learning model that use experimental information. And this experimental information, as far as, at least as the Curie temperature, typically are extracted manually. So it's hard work to put this database together. I mentioned that because recently we've been developing an automated pipeline with which we can extract information from literature. And in fact, now we're constructing a second database of Curie temperature, which is entirely automatically extracted using machine learning. So essentially, we screen about 250,000 articles to extract about 1,700 or so Curie temperature. So this is like, it's a small diversion, just to say that we are now developing technique to extract experimental information, not just VTC, from literature that will eventually speed up the use of machine learning model on large experimental data set. Okay, going back to the problem we have at hand. So what we really want to find out is, can I construct a model to predict Curie temperature for ferromagnets, which is actually efficient and simple? Now, in principle, you don't really need to do machine learning, okay? So you can use electronic structure theory, and the standard way that typically people use to predict Curie temperature for ferromagnet is essentially the one you see here. So essentially what you do, you start from your electronic structure theory of choice, which typically is density functional theory. You do a lot of total energy calculation for different magnetic structures. You map this onto some model, typically an Heisenberg model of some kind. And then you do Monte Carlo, classical Monte Carlo simulation to calculate the Curie temperature. And now, if you look at this pipeline can fail more or less at any step. It can stay at the step of density functional theory because you know, there are a lot of approximation to density functional theory. Typically, you need to have, in some cases, very large simulation cell to simulate very long range coupling. There is an issue of how you interpret broken symmetry solution and so on. So there is error that actually built at the electronic structure level. There are errors that built at the mapping level, because if you have excitation which are not spin waves or magnon type, the Heisenberg model is not of great use. Typically, you have to cut the interaction range. So even when you map on an Heisenberg model, is usually incomplete. And then also the Monte Carlo level, you have quantum effect and so on. So the bottom line here is you have a method that actually can fail anywhere. And I would say the real message here is that typically when you do this in this way, if you don't really know the answer, it's really difficult to make a prediction. So if I give you a completely unknown magnet, I might have guideline that this method might work, but actually might fail, and might fail significantly. So it's not actually a good method to do blind prediction, in addition to be expensive. So actually what we decide to do is something quite different. And the idea is, can you use machine learning model? So can we try to use experimental data to predict Curie temperature of magnets? And essentially the idea is quite simple. What you do is we have available this database of Curie temperature. We need to find out a way to encode a chemical formula into a vector that actually we can use to construct the machine learning model. And then we try to train the model to predict the Curie temperature. And the way we encode the chemical formula is very simple. We have a vector which is as long as the element in the periodic table. And essentially what you do, you write at the entry corresponding to the atomic number of your of the element in your magnet the atomic fraction of that particular element. So for instance, if you want to encode Fe3O4, you're going to write 4/7 for have a position 8 for oxygen, and 3/7 have a position 26 for iron. And you do this for the entire data set. Now, you find out that some entry in this vector are always 0, take the noble metal, for instance, and then you eliminate all those. But then you have a relatively compact representation that with about 75 or so entries can describe any possible chemical formula for magnet. And then essentially what you do, you run a machine learning model. And what you do, you typically, for those of you who are not familiar with machine learning, what you typically do, you separate your data in a training and a test set. The training set is used to train the model. The test set are data that the model has never seen before that is used to test how good your model is. And what you typically do, you do this as a function of the amount of data that you have in the training set, because of course, if the model knows all the data by hand, it will do very well, but it will not predict anything. If the model does not know enough data, it is not going to be able to make a prediction. So there is a sweet spot where the error on the training and on the test set are similar, which essentially means that the model has probably learned something. Okay, so we do this for the Curie temperature. And as I said, we try many different models, and I really want to cut short here because, I mean, if you have any question, I can answer later on. But what we found that typically deep learning method seems to work much better than regression type of methods. All this symbol here, C and so on, that you see are all possible feature reduction techniques that we try. None of them seem to work very well. The bottom line that we found is that the best model are the one where you consider all the information in the training set. So essentially all the, you don't do any feature reduction. And we found that the random forest model is by long distance the best with an R-square coefficient of the order of 83% or so. R-square is the goodness of your model, and essentially 1 means a perfect model, okay? Now, let's see actually what this model gives you. So what I'm plotting here is a diagram where I have the experimental Curie temperature against the predicted one by the model for the test set. So for data that the model has never seen before. Now, perfect prediction will line this data on the black line. So of course the model is not perfect. However, you can see that the trend are actually quite nicely reproduced. The average error on the Curie temperature is on the order of 60 Kelvin or so, which is not that much. And probably it's not that much because certainly allow you to distinguish magnet which has a low TC from magnet which has a high TC. So if as a hard predictor this is not perfect, certainly as a classifier between high TC and low TC magnet, this actually does the job. The other thing I want to mention actually that 65 Kelvin as an error is actually far lower than actually what you can expect if you do the standard procedure that I showed you before in a completely uneducated way. So if you fix the electron structure theory, the Monte Carlo and so on, and you run through this 2,500 material, you're going to have an error which is significantly higher, okay? Yeah, I skipped the comment on those two. Now, so let me show how the model then works, okay? So here, what I show to you is the model in action against 3 different binary phases. And the way to read this plot is the following. For each one of these binaries, so this is cobalt, manganese, iron, nickel, and nickel, rhodium, the cross, the black cross, are the data that has been explicitly included in the training set. So are the data that the model exactly know about. The blue line is the prediction of the model. The blue shadow is the uncertainty on that prediction. And the green dot are experimental point that the model has never seen before, okay? And let's look how this works. So if I start from the first one, this is nickel rhodium as a function of a nickel fraction. So 1 means pure nickel. And then if I go to the left, I go to the rhodium side. And essentially, what you find that nickel rhodium form a solid state solution, and this solid state solution has a TC that decrease more or less linearly with the rhodium concentration, and the entire things become paramagnetic at about 0.6 or so, a little bit more actually, 0.7 of a rhodium fraction. And the model actually quite nicely seems to know that as the rhodium concentration, the error become larger, because of course there is not so many magnets with rhodium, so the model actually couldn't really possibly know what happened when you have a lot of rhodium in a magnet, but certainly the trend is actually well predicted. And you may argue, okay, fine, it predicted a straight line. So then I can go to cobalt manganese. Cobalt manganese is interesting because now the model knows about two points, pure cobalt here, and this 70%, 70-30 structure down here. The TC more or less goes straight between these 2 points, and the experimental TC also map quite closely. The model has little error, and despite not have this point specifically used for constructing a model, simply because there is a lot of phases with cobalt. So actually, the model knows about the physics of cobalt, even though it doesn't know specifically the physics of cobalt manganese. Now, what is interesting, that I found personally interesting, that then the model has the TC seems to go back up after you pass this critical point. Now, here there are no experimental point, not because there aren't, but because on this side of the cobalt composition, you find antiferromagnet, not ferromagnet anymore. And we don't use the antiferromagnet. So somehow the model seems to be aware that the TC has to go up for this large manganese concentration, although, of course, wasn't trained on the antiferromagnet. Now, the most interesting I found is this one here, is iron nickel. Now, iron nickel, as you see, has quite a complex behavior with the composition, because actually it's a structural phase transition. So you go from FCC to BCC along the way here. And what you see is that the model is kind of able to follow the trends. There are some points along this curve. So actually the model knows somehow about these trends, but nevertheless is able to follow quite nicely. As a larger error here, where also the prediction is less accurate, but it is quite narrow actually in this region. The point I want to stress here is this point here, where I have green and red point. So these actually are two experimentally known polymorph of this iron nickel phase. One is a 3,1L21 structure, and one is solid state solution. And those two can coexist, depending on the growth. The model, of course, knows nothing about structure. So actually, it tried to cut across a straight line between these two polymorphs because it doesn't know anything about the structure. Now, he gets the rough Curie temperature of both of them, but he's not able to distinguish. And you can extend this analysis to ternary compound. So this is for aluminium iron cobalt. Aluminium iron cobalt. And I don't really want to spend too much time because it's essentially the same drill as before. So you can look at the binary composition along the edges of this triangle, but also you can look at ternary composition in the middle. And again, when you see the dot, these are experimentally known structure, while the color code is the predicted model predicted Curie temperature. And as you can see that the model again is actually not perfect, but is quite good to describe trends. So I guess the kind of a take-home message from this first part is that you can construct models which are just based on data. So when we published this paper, I was pretty proud because, strictly speaking, this has no real calculation, right? So we didn't run any DFT or anything, electronic structure theory calculation. It's just data. So we just look at data. And this is typically very useful to do a very large initial exploration, because once the model is constructed, it takes nothing to run it. So the throughput is extremely high. Now we can explore widely any sort of stoichiometry come to mind. And these all just need experimental data. So not much theory.
Stefano, I have a question. Please, I don't interrupt. Like, if you go back to the models themselves, when you look at the one of the nickel, iron nickel, you do have more dots that the data knows about. So essentially, this complex behavior, how do you decide then, the crosses that you chose in there, there's more than the one in the cobalt manganese and the nickel rhodium. Is that ahead of time that you look for it, or how would you choose the number of dots to tell them about the complexity?
No, okay. So here right now, that's a very good question. So here we use only the crosses are used because actually those are all non-solid state solutions. So actually we use only the stoichiometric compound. We didn't use the alloy at different compositions.
But for example, if I took some of the crosses out of the iron nickel,
Yes.
that it was known, would it do as good of a job or less of a good of a job?
Oh, I see.
Because right now, if you just look at the crosses and I make a lines, you know,
Yeah.
the crosses are telling me more the lines what to do. If these are the original things that they know about, then I say, okay, I can guess the line, maybe not the one on nickel rhodium, because I don't know which way to go. But the iron nickel, this complexity seems to be dictated by where the crosses are.
Yeah.
And if
Right.
it's a restriction, then you know, to what extent can you test that, or to guide you when you don't have that guide?
Yeah. So I mean, so here, right. So here, essentially, what we have is we have you know, iron, nickel, this L21 phase, and I'm not sure actually what this might be. Some the other crosses are some other intermetallic. No, I mean, okay. So the reason actually why we didn't select the different alloy. So okay, we didn't do the test if we start removing crosses where the model will go. Okay. Bear in mind that the model knows about trends, not just through iron nickel, but through all iron with all the other transition metal that has been involved. So somehow this transfer knowledge actually from other phases that actually goes here. The reason actually why we didn't include other data, so I mean, in principle, we could include all the green point as well, right? It's because actually, typically you have a lot of data for very tight chemical composition, and it's completely imbalanced the data set. Here, essentially, what we want to keep as much diversity as possible in the data set, because essentially we can construct much more tighter model for specific alloys that will predict much better, but then they won't predict anything else. Right. So here the idea is, okay, if you give me a stoichiometry that come on the top of your head, are we able to give you a TC which is actually in the right ballpark? That essentially was the exercise. Okay. So yeah.
So I just wanted to because it came in my mind and then I forgot.
Yeah. No, absolutely. Oh, that's a good question. Yeah. Okay. So no, I would say so this is useful because if you want to do a very large exploration, so when you have a lot of possibility and not enough throughput to do everything, is the model need data, and these are experimental data which are way more difficult to harvest than the theory one. Theory data are easy because we all have standardized DFT code that actually where we can dump data in a database, but experimentally we need to mine them, typically from literature. And data automation collection is the way to go. And then I just want to mention that the structure is difficult to include. We spent quite some time to try to have structural information, and with very little success, I have to say. Now, okay, let me try to go to a second type of method. Now, here the idea is, assuming we know what atom are we dealing with, where should I put this atom to magnify a particular property? And now, and to explain how this works, of course, now, if the question is where should I put the atom, I need to have a way to represent the atomic position. So, and as we saw in the example here, different structure give you different property, even if the chemical composition is the same. Now, if you think for a second, a lot of the way as a physicist we like to categorize structures are not terribly machine learning amenable. Think about the space group, right? These two structures have that look identical to naked eye, have very different space group. This is a cubic one. This is a oh boy, I don't remember what it is, but anyway, it's a lower symmetry space group, which actually you go from this structure by pulling those
rhombohedral.
Rhombohedral, right? Thank you, Igor. By pulling these two corners, and this actually I pulled those two by 1%, and of course the property between these two cannot change drastically, although the space group changed massively. So if I want to categorize these two materials just through the space group, I don't have a continuous measure of how the property change across the space group. So a better way would be to try to represent the actual position of the atom. And this is not so trivial either. And I just want to explain how we do then the representation. So let's suppose you want to represent this molecule, okay? And you know, one thing comes to mind is, okay, I can represent the molecule in Cartesian coordinate and I'm done, okay? Now, of course, this is not so good because if I translate the molecule, the Cartesian coordinate change, and a machine learning model at the end of the day just take vector and try to rationalize structure between ensemble of vectors. And of course, translation means that if you add to a vector any arbitrary vector, you have any possible vector, and the property remains the same. So somehow you need to construct representation which are invariant by translations. And typically, the way we do it is to assume that the property you want to calculate is local in space. So in other words, that the representation of every is the property is the sum of the properties that can be attributed to each single atom, and then you can use the reference frame where the single atom is at the origin as a reference frame, and then you achieve translation invariant. So if the quality is not local, we have a problem, but for a lot of the things we're looking at, local quantity are okay. This concept of locality fixes another problem, which is the one of invariance with respect to the permutation of atom. So if I label the atom in a different way, but I sum the contribution of each individual atom separately, it doesn't really matter in which order I label the atom. Now, the second property that you really need to include if you want a representation useful for machine learning is rotational invariance, because of course, a molecule rotated is still the same molecule, although their coordinates are different. And this is actually not so simple to do it. I need to be done by hand. And typically, you need to construct the representation to include rotational invariance. And the typical way to do is to expand the position of the atom with respect to the local reference frame into a spherical harmonic expansion of some kind, or representation that contain the same information. And just want to give you one quick example of how you do that. So let's suppose you want to represent the position of the atom around the blue atom here. So essentially the function you have to represent is a collection of delta function centered on each one of the yellow atom, eventually with a weight that can be the atomic number, for instance. And what you can do, you can expand this density on the linear combination of spherical harmonics. And if now you sum up over the third component of the angular momentum, you have a quantity which is known as the power spectrum, which is actually rotational invariant. And this is, for instance, is actually a quantity that has been used for many, many years in image processing, in three-dimensional image processing. And so this is the spirit of the construction of this rotational invariant quantity. Now, the way we use it is actually more complicated, and I just put this slide to show you that, just to give you an outline how we do it. So essentially, what we usually do, we expand this local environment over the four-dimensional spherical harmonics, and you take a stereographic projection of those four-dimensional spherical harmonics. This goes a little bit in the technical side, but the reason you do that because you can include in an angular variable also the information about the distance between two atoms. Anyway, I think you don't really need to know that. What we do then when we have this spherical harmonic expansion, we construct a triproduct of the coefficient of expansion, which are known as the bispectrum. These objects are rotational invariant and are effectively many-body descriptor up to 3 bodies. So essentially what we have an intrinsic many-body description of our local environment. Now, we pay the price because this is a relatively complex construction to make. But then because the representation is complex, we can represent quantity with a linear expansion. So typically what we do, this B coefficient, if you like, are the abstract representation of your chemical environment, and then any quantity is expressed essentially as a linear combination of those descriptors. And in particular, we construct ridge regression. And for instance, if you want to expand the total energy, the total energy is the sum of the contribution of atomic energy, and each atomic energy is obtained by an expansion over this particular basis. So that's essentially the kind of the outline of what we want to do. And essentially now, this is an extremely accurate model, and is, for instance, very accurate for energy. So here, for instance, I'm going to show the total energy of this particular molecule is a cobalt-2 single molecular magnet. And the way you typically train this type of models are you do a bunch of total energy calculation from DFT, you do the first interpolation of the model, then you run a little bit of molecular dynamics, and you monitor whether the molecular dynamics is still well predicted by your model. And if not, you include more configuration and you retrain. And essentially, once you're done, you can calculate anything you like, phonons, phonon-electron coupling, total energy, and so on. Now, and these are the typical error you get. Again, this is a parity plot, so predicted energy from the model, total DFT energy. This is actually for the entire molecule. Total energy with error in the region of 70 millielectron volt. Honestly, because we didn't push very hard, you can push to probably in the region of sub-millielectron volt per molecule, which is essentially as low as you go with DFT. So, strictly speaking, the model can reach accuracy which are comparable with the original electronic structure theory you have. Now, why? And okay, so this is an example of. And because everything is very general, it doesn't really matter what is the chemical bond. So, for all sorts of possible different coordination, you achieve always the same error. And as you see, you can push the error to extremely low values. Now, why actually I mentioned this in the context of magnetism? Because actually, as I mentioned, this model can be used to predict quantity which are not necessarily energy. So here, for instance, we use the same model to reproduce the uniaxial anisotropy constant of this particular molecule, which is a uniaxial molecule. And two things I want to mention here. So all these points are the value of a D constant, of a zero field splitting constant for this particular molecule as a function of distortion of the molecule itself. And as you see, again, this is a parity plot. And so the predicted value from the model are essentially at par, this time not with DFT, but this actually were calculated at the post artifact level, particularly at the CAS-SCF level. So essentially what you can, this model is extremely versatile because it can be used for quantity, for local quantity, different from energy, and at any level of theory you like. So if you can afford wave function method, this can be used also for wave function method. Now, why I'm saying all this? Why is this useful? Because now we have models which are super efficient, okay, and are super fast to run. So what I can now construct, I can construct this as an optimization problem. And for instance, I can ask the following question: how can I distort this molecule to increase the magnetocrystalline anisotropy without changing the energy too much? And essentially what I'm doing, I'm constructing this functional where this is the total energy and this is the uniaxial anisotropy, and Q are all the coordinates of the system. So in these molecules, there are about 90 or so coordinates because they contain about 30 atoms. So if I want to optimize this function, I need to optimize a space which is 90-dimensional. Of course, it's impossible to do with electronic structure theory, but it's possible to do with this model. So for this particular case of a molecule, what we run a swarm algorithm to explore this complex potential energy surface. And what we found that a 5% reduction of the distance between cobalt and nitrogen, which is the ligand in the first coordination shell, and an alteration of about 5% of a cobalt-nickel bond angle, which is actually something you can achieve by engineering appropriately the ending the functioning group at this molecule, can increase the magnetic crystalline anisotropy by about 50%. And you can start to play this game with extremely complex optimizations. Okay, so very quickly, just to summarize this second part, you can construct extremely accurate atomic models, which are not limited to energy, but are limited to all possible quantity. This can be used in combination with molecular dynamics to look at finite temperature property. but actually you can use also as an exploration and as a design tool, as I show. Typically, this work a little bit better than for molecular than solid, and this is an initial representation of how the data structure is constructed, and there is risk of overfitting. So you need a little bit careful when you fit these models, and also at least this class of models are not so easy to interpret. So it's not easy to understand exactly what the descriptor of a particular structure essentially means. Now, the very last thing I want to do in the, I don't know, 5 minutes or so that I left with is to see whether I can extract the concept of these machine learning models to spin quantity. So in other words, can I construct machine learning potential for vector fields, not scalar field? So at the moment, the only information I have is the position of the atom, but the question is, if the atom bears a spin, now I have a distribution of errors, now not a distribution of scalar. So can I do this with a vector field? And very quickly, the answer is yes. So the idea now is as before. So I represent the local spin structures through essentially a density distribution of spin this time. And what I construct this again in terms of spherical harmonics, where now I have a different contribution. So I have a radial function that describes the distance between the atoms, a spherical harmonics that describe the actual position of a particular atom, and another vector, another spin that describe actually the value of the spin of that particular atom. What I can do, I can combine this in a total spin, and again integrate over third component of a total spin. And then I have a representation which is for a vector field that is rotational, which is a rotation invariant. Now, so this is, if you like, it is a generalized power spectrum to a spin vector field. Now, here what I'm showing is just demonstrating that this is rotation invariant. So this is this power spectrum calculated for this pyramidal cluster, and I just rotate the cluster, and you see that the power spectrum, this is the power spectrum, is independent of the rotation of the cluster. And the other thing I want to mention, which is interesting in this model, that this descriptor, the zero order term of this descriptor, describe a spin-spin Heisenberg type of interaction. So this representation naturally has built in the classical Heisenberg model. Now, why this is interesting? Because now I can construct a machine learning force field for spin, and where I have the freedom to change the direction of a spin, the magnitude of a spin, and the position of the atom. So actually, is a model that universally can treat on the same footing transverse excitation, longitudinal excitation, and spin phonon coupling. And for the moment, we test the model on another simple model. So we construct a slab of iron, and where we have a spatially dependent Heisenberg model, and we have, if you like, a Landau type of Hamiltonian for the longitudinal spin excitation. And what I'm going to show here is the result of how the model can predict energies of this empirical model for magnetism. And this is a quite sort of a busy graph, but I guess the only thing I want to show, the only take-home message I want to give you is that typically with extremely little information, so extremely limited number of training points in the range of a couple of hundred, and an extremely compact model, so there was only 35 or so unique descriptor, you can achieve extremely high level of accuracy. So this is again the parity line for a model for energies where this corresponds to different spin arrangement, different atomic arrangement, and different magnitude of the local spin. Now, when you have a severe longitudinal spin excitation, typically you have to include no linearity in the model. So what we do is, instead of using linear regression, we use, in this case, a kernel-based model to reproduce the energy. but this is just a more technical detail. So the presentation contains all the information. The physics you want to extract, if there is a nonlinearity, you need to build in the nonlinearity, and in this case, the way to go is through a kernel model. The last thing I want to show you is that this is, of course, not only valid for model predicting other models, but you can go back to your electronic structure theory. So here, what I'm fitting is now data from DFT. So the red, so the dot correspond to different configuration of either alpha or epsilon, or so BCC or HCP iron in different atomic configurations. So for different distortions. And I guess what I want to show here is that if you try to fit with the model with where no spin information, you get the blue point. So essentially you cannot fit. But if you try to fit the DFT data with this spin power spectrum, where we have a full description of the vector field, you have an extremely good fit with error in the region of 10th milliev per atom or so, which again, I mean, can be further reduced with a little bit more data. Now, what we are trying to do now is to take this model and then plug this into Monte Carlo, also a simulator, to try to have thermodynamic property. Now, what I really want to stress is here you have just point. So whether this point corresponds to an atomic distortion, to a spin wave, to the effect of a spin phonon coupling, or to a longitudinal or to a Stoner type of excitation, actually is irrelevant. The model actually describes all those possible excitation on the same footing. Okay, so I guess to finish, I hope I convince you that you can extend all this concept of machine learning force field to vector field, and you can do this in a way which is completely agnostic. What is the physical origin of your potential energy surface? We did the power spectrum. We extended also to the bispectrum. Typical small training set are needed, and this concept is extended to other force field classes that we are developing at the moment. You need typically nonlinear model if your physics is complex, but again, this is typically not a problem. Now, the only piece of kind of warning, which is actually more serious, that typically the construction of a data set is not so simple, because you need to run DFT calculation that explore nicely this potential energy surface. So there is a little bit of, if you like, blackout in constructing this data set. Okay, to conclude for real, what is the bottom line here is I hope I give you a good account of what machine learning can do for you. This has been limited a little bit to magnetism, of course, but essentially the same method can be transferred to other problems. There is quite a lot of other stuff we're doing that, for reason of time, I didn't have the time to explain, but this is a fast-growing field. Now, it's fair to say that it's joining different fields, solid-state physics, quantum chemistry, data science, and so on. So strictly speaking, at the moment, we know some direction, but we don't know the full story. So I would say we know how to go from A to B, but probably the entire picture is more complex than what we think about at the moment. And with this, yeah, thanks a lot.
Excellent. Thank you very much. The opens for questions. So then let's see, hang on a second. Helena, Igor, go ahead and ask your question. I think Anna, I don't know if you wanted to ask a question.
Actually, there was a question in the chat which we had a little discussion, and I guess if Alexander allow me to read his questions, he asked what happens with the model at small nickel content in nickel rhodium. Does the TC go to 0 or does it remain non-zero? And in fact, I can probably even expand this question a little bit if you go to this right. So naively, I mean, playing devil's advocate, you can say that except for nickel rhodium panel, for all other cases, just linear interpolation does as well as machine learning or even better. nickel rhodium is a different case because you have only one point. So the first question is, does your model know anything at all that rhodium itself is non-magnetic? And if it doesn't, where would it go for low nickel concentration? Would it eventually hit zero or not?
Yeah. Okay. So I have to admit that I don't remember how the curve continued, to be completely honest. I mean, I would say, but the point is this, right? That the shadow area here is the uncertainty of the model. So I would say from 0.7, the model goes to zero within the uncertainty of the model, which actually, as you see, so the shadow area grows as you go more towards rhodium because knows less and less about rhodium. So
the program had never been taught before that rhodium itself is non-magnetic.
Yeah, no. I mean, so to be honest, it might know of some other magnet with rhodium. I don't know what honestly what else it was with rhodium. I mean, my guess is that he knows about this behavior because probably he knows about some other nickel and transition metal phases. So he probably knows something about probably nickel platinum. He probably knows about the fact that actually as you increase a 5D element, a kind of a noble 5D element, this has to go down. Probably he knows about that, but he doesn't know anything else. Probably very, very little about rhodium itself, I would say.
Okay, then if I'm allowed, ask another question. Of all other things that you were calculating, there's one which is really easily available from DFT calculations, and that's equilibrium magnetization. Did you ever think about feeding your model with experimental information and calculated equilibrium magnetization at zero temperature? Maybe that would improve your prediction power.
Yeah, so I mean, you mean to couple the knowledge of equilibrium magnetization with the TC, you mean?
Yeah, well, I mean, you have experimental data on TC and on various other things like structure, and that's the only thing that your program uses now. But there's one thing that you can easily calculate for any material, basically, is DFT equilibrium magnetization. Yes. And that maybe that would improve your if you know that this that DFT predicts very small, like for instance, this case, DFT would predict, say, rhodium nickel 50-50 to be non-magnetic, and that would improve your prediction power.
No, I mean, no, absolutely. So I mean, okay, we haven't done it, but no, you're absolutely right. I mean, we have. I mean, in fact, on another project, we are doing this very large high throughput database. So essentially, we probably have the GGA equilibrium magnetization for more or less all this. I mean, the vast majority of this magnet.
Right.
We never tried to do it because, okay, so at this level, we want just to keep the experimental information in, and we want to check how far we can go with experimental information. But I think you're absolutely right. I think probably I mean, more information is the merrier, and I think anything which is easy accessible from DFT, like level magnetization, absolutely. Yeah.
Okay, thank you.
Yeah, I think, yeah, absolutely, yes.
So I'm not sure if you had a question, Anna, or you had your hand up, or just simply that you like to talk. Sure.
I just like to talk, and I would like to give an applause.
Okay, no problem. So I have a question a little bit. So you've been, like you said, in this case, kind of like accelerated material discovery based on recognition or model, these typical algorithms from AI that we now owe my life to myself because it's translating all my documents, German documents, very accurately. Now, let me turn it around the other way. So now you are saying, okay, I know the properties I'm looking for, and I'm going to look for the material that has this particular enhancement of the properties, etc. This is something where you know what you're looking for. It's just telling you new material that you may not have thought of, but you have been talked a long time to get to, but it's still no new, not to say new physics, but no new things in there. How about the other way around, where you say, okay, look, I'm now searching your databases and recognition of particular properties, and look at correlations that would not have been found or looked at or thought of even theoretically to say, okay, is there any connections that before we wouldn't have thought of, where it's actually physics phenomena discovery, not materials discovery, that it will hint to. And we understand, of course, that correlation does not mean causality.
Yes.
Same thing as you will correlate that way. The fact that you eat ice cream and you drown if you look at that's not what you're looking for. That is not careful what you're telling you. But sometimes is there a possibility to turn that around to help us? For example, when the discovery of the topological phases or other things that could have that being observed. Or, here we have our own story of altermagnetism. Could a search of this sort have sped it up, or do you always need that other analytical breakthrough?
No, I mean, okay, I guess this is a great question. I would like really to have the answer. No, I would say, we have available nowadays, I would say, databases with several million prototype structures, where, forget the machine learning for a second, kind of DFT calculated prototype structures, which typically include, I would say, a good 70–80% of known compound plus millions of hypothetical ones. So I would say that probably there is enough data to start to do exactly what you want. So to say, look, can we start to go around and see whether new physical insight come out of this very large data structures? I would say the tricky question is actually how you formulate the question. So essentially, how do
you teach him what is an insight?
Right, precisely. So how you interrogate the database? Because at the moment, essentially, what you can do very nicely now, you can validate the theory. So let's suppose you're looking at, I don't know, a delta Dirac crossing. Then you scan 3 million band structures until
you know what you're looking for, and you're finding it in a more efficient way. That's clear.
Yeah.
I'm just saying, okay, can you find your needle, and then in the
I think there are methods to. In machine learning, there is a full class of methodology which is called unsupervised learning, where actually you try to have the method that guide yourself in the search, right? As far as I know, very little has been done. We never done it. So we always try to formulate the question first and then try to run through the data we have. Let's say my most honest answer that I never seen done it, and I wouldn't know how to do it, but I think it would be a very interesting. I suspect there is things to learn.
There could be a lot of nonsense coming out of it, of course. There's no question about it, but yeah, at some point this has to be turned around to not just look for efficiency, but also it's a bit scary, right? Because I can say, I'm going to figure out something that you don't figure it out, and then I figure out that you're not needed.
Of course, okay, the model are as good as the data are. So essentially, you have this is done at DFT level with all the problem DFT has and so on. But I would say even that, so there is noise, but even that, I think actually would be interesting to see, for instance, can you go through the band structure and find something very anomalous, something that never seen before for whatever reason, right?
Or identify it as not as an anomaly, but later on look for that anomaly in others and identify that is a phase or that is something that is more general.
One thing you can try to do, you can try to cluster data. So you can try to construct, there are different ways to construct algorithm where you cluster data in groups, and you might find something that don't belong to anything. And maybe these are the interesting one. I don't know whether anybody has ever done it in a, finding anything. I think would be interesting.
Divo, you have a question? Divo?
Yeah, I really like the talk. I just have several questions on maybe following this interesting discussion. When you were showing this 2,500 ferromagnets, and this was experimental data. So in the experimental data, the magnets are in principle also correlating. There are many effects which are beyond the DFT. So when one uses your algorithm, could you predict some additional informations which are trackable by the algorithm, but not by the band structure? So let's say whether it's metallic or insulating ferromagnet.
Yeah. I mean, so if in principle, you can, if you have a data, you can construct model that actually predict this data. So say for this, yes, if I have information about metallicity of this 2,500, certainly I can construct a model that say classify between metallic and non-metallic. If I have enough data, I can even predict gaps. So there are actually few studies where people construct, gaps, experimental gaps usually is a strangely defined quantity, because sometimes it's the transport gap, sometimes it's the optical gap, and those are all different and so on. But people, for instance, construct a machine learning model to predict the GW gap across a bunch of material, and this typically work okay. So you have good predictors. So certainly you can construct models, but depending on the property can be tricky. So for instance, you mentioned correlation, right? So the reason why we start from ferromagnet, because we know that in antiferromagnet, the correlation typically is much more nasty, and you can have, in antiferromagnet, you have this situation where you distort a little bit and everything changes, right? Or you change the doping by a tiny fraction and everything changes. And this actually, unless you have a very good way, for this to include the structure, antiferromagnet are much more tough to describe. Yeah. And I'm pretty sure that if I construct people have tried, but I'm pretty sure that if I construct a classifier that distinguish ferromagnet from antiferromagnet, the classifier will try to put all the oxide in the antiferromagnet and everything else in the other box, because it's the easiest thing to do, essentially. And my feeling is that there are not enough data to construct models which are much more accurate than that if you go to these fine properties. So, yeah.
Do you know how many insulators are out of this 2,500 ferromagnets?
Not on the top of my head, but I can look. I suspect there is more metals than insulating, but I don't know the number now, but I have it. Yeah.
I mean, practically none.
Yeah, possibly. Yeah.
But then, really none.
I don't know. Maybe no. That's not necessarily. I mean, there are a few examples, but they are ferrimagnets, not ferromagnets. Yeah. So basically, uncompensated ferrimagnets, which like magnetite, for instance, they're considered ferromagnet, I think, by this qualification. But real true ferromagnets, when all spins are parallel, I don't know any, in fact.
Yeah, no, exactly. Yeah.
So which publication is it from, this nice graph?
This one here. Oh, hold on. I think it's this one here that you see on the bottom, actually.
Awesome. Okay.
Yeah. Okay. I mean the histogram, you mean?
Yeah, the histogram.
Yeah, I think it is in this one here. Yeah.
Mm-hmm. Thanks. I'll take
some version of it. Yes.
Okay. I think it's a question from Igor Sandalov. Go ahead, Igor.
Okay. Thank you. I have actually two questions. One question is connected with previous discussion, and probably it's somehow should be described as difference between learning machine and artificial intelligence, because you need, in order to predict something unknown, you should have opportunity to include something unexpected, some coupling, some weights, and probably something random. In this model, it's one question, whether you think in this direction somehow.
Yeah, I mean, I think this model that I show, I mean, this one here for BTC, really what is good at is I mean, essentially at this level is to find trends in data that live in a highly dimensional space, where essentially, for the human, we find trends in something typically in low dimensions. So we're not used to thinking in many dimensions. And I think what this model really do is actually finding trends. Whether the model can find a needle in a haystack, probably this level of model, no, I would say. Because I don't think they've been trained to actually find a needle in a haystack. And actually, it's very difficult to do it when you have not so much data available. Because, okay, at the end, this was trained on 2,500 compounds, which by any stretch of imagination is not big data. So if you think about, the language model that Google and and all the guys are coming up with, these are based on the entire corpus of English literature for this. And so, I mean, the amount of data is ginormous. I think, now here it's really essentially, I would say, the benefit of this is that you rationalize high dimensional data in a way that would be very difficult to do for a human. But I don't think it's actually, this really allow you to find the needle in the haystack, let's put it this way. I mean, I think what you can find is, you can find that for some compound, the model looks extremely confused, which essentially means if you have a material for which the model absolutely doesn't know what to do, maybe it's interesting because it's probably very new. But I think beyond that, I don't think it's so easy. Yeah.
Okay. And the second question, all your models assume that each atom has some local spin. And actually, this is a kind of restriction, I think, because actually it's not obligatory. So first, and second, if you want to describe, for example, difference between antiferromagnet and singlet state, real singlet state, then you simply don't have these parameters in the model, right?
Yes. Yeah, no, absolutely. So I would say, so yes, so essentially this describes, if you like, classical spin field, right? Not so you're absolutely right. So it's a broken symmetry or a true singlet are equivalent in this case. Now so in terms of single spin on atoms, it is true that, I mean, this describes single classical spin on each atom, but actually now we have, it's a different class of model, it's more based on cluster expansion, but we have a way also to represent a full spin density over just a three-dimensional space. So where you can have, so essentially we have models, we've constructed a cluster expansion to essentially predict the result of a DFT calculation. And this is also for non-collinear spin polarized. So essentially what we can do, we can say, okay, we can produce by a model the non-collinear spin density result, which is the result of a non-collinear spin calculation. So in principle, it is generalizable to densities, but the other problem that you mentioned about, yes, to do singlet, no, we cannot do it. Yeah.
Okay. Thank you.
Okay. So I think that's all the questions.